Hi, I'm Scott from Luna Innovations. I support our optical communications test product lines, including the Lightwave Analyzer. In our last video, we walked through unboxing and setting up your Lightwave Analyzer. In this video, I'm going to walk you through taking your first measurement, as well as going over some of the software settings that are pertinent to most measurements. The goal of this video is to help you get the most out of your Luna Innovations Lightwave Analyzer. As a disclaimer up front, in the spirit of continuous improvement, Luna is continuing to refine and improve our software. So the screenshots shown in this video may be slightly different than that of your system, depending on what version of software your Lightwave Analyzer is running. Software updates are available for download from Luna's website. Today, what I'm going to be measuring is a simple fiber network. To start, I have a 1 meter long sacrificial jumper and adapter cable, which has an FC-APC on the end that connects to the Lightwave Analyzer, and an LC-PC to connect to the cable under test. Then, I have a 10 meter long LC-PC to LC-PC cable. This cable was purchased as a standard off-the-shelf cable with a nominal length of 10 meters. Off-the-shelf cables are almost never the exact length specified, so in this video we're going to measure exactly how long this cable is. Then, after the cable under test, I have another 1 meter long adapter cable with an LC-PC to connect to the cable under test, and an FC-APC connector which is serving as a terminator. While the terminator doesn't need to be an FC-style connector, it should be an angle-polished or APC connector to make the transition from glass to air. This is important because the Lightwave Analyzer is very sensitive to bright reflections. Having a bright reflection at the end of the measurement, such as the reflection from a PC or UPC to air transition, will make taking measurements and interpreting the data much more difficult. Other methods of terminating the fiber to be measured include coiling the fibers into a tight loop around a mandrel, or using a commercially available black hole terminator. Usually, these black holes have a length of coreless fiber in them that dissipates the forward light energy with minimal back reflection. Before we connect our network to the Lightwave Analyzer, we first need to choose the length mode that we are operating in. As my total network is only about 12 meters long, we can work in 20 meter mode. Other length mode options include 50, 100, 200, and 500 meter lengths. Some of these lengths are optional upgrades, so you may not have all of these modes available on your Lightwave Analyzer, depending on which options you purchased. The next setting that I would like to discuss is the group index. The group index is a decimal number that represents the ratio of the speed of light in a vacuum compared to the speed of light in another medium. In our case, that medium is glass. For single-mode fiber, a common group index value is 1.4682. That means that light in a vacuum travels 1.4682 times faster than light in a single-mode fiber. The reason that this is important is that the Lightwave Analyzer fundamentally measures time of flight, not distance. Distance is then calculated from the time of flight using the group index supplied by the user. The best place to find the group index for your fiber is on the datasheet provided by your fiber manufacturer. The fibers I'm using today have a group index of 1.4682. Let's set that parameter in the Lightwave Analyzer software. The next thing to configure are our x-axis units. The Lightwave Analyzer can display the x-axis in millimeters, meters, inches, feet, and nanoseconds. If you do not know the group index of your fiber under test, or if you know that the group index changes along the optical path, measuring in nanoseconds eliminates the dependency on the group index value. This can also be useful to customers who are concerned about directly measuring latency. However, today I am interested in measuring length in meters, so let's change our x-axis units to meters. At the same time, let's change the return loss integration width to 1/2 meter and the insertion loss integration width to 1/4 meter. Now that the Lightwave Analyzer is configured, we can clean and mate up the optical connections. Now that we have our optical network connected to the Lightwave Analyzer, our group index and x-axis units set, we are ready to take a measurement. To do so, simply click the Measure button. The instrument will take a measurement and display the result on the screen. Please note that longer length mode measurements may take longer to complete than shorter length modes do. The Lightwave Analyzer measures reflectivity as a function of time of flight, which can be calculated and displayed as physical lengths. Those of you who are familiar with interpreting an OTDR plot will likely find the Lightwave Analyzer plot similar. You will see peaks that correspond to reflection loss when going through connections, as well as the Rayleigh scatter, which is a distributed minute reflection off of the crystalline structure of the glass. Let's study these features more using the vertical cursors. As my goal today is to measure the length of the 10-meter piece of fiber, I'm going to use the vertical cursors. Drag the solid cursor to the start of the 10-meter section and the dashed cursor to the end of the 10-meter section. If the peak is within the shaded integration region, then you can click and the cursor will jump to the brightest reflection within that shaded region. We'll do that for both the start and the end peaks. In the upper right corner of the screen, we can see the x-axis values for both cursors, as well as the difference value, which is the difference between the two cursors' locations. We can see that the solid cursor is at 1.0894 meters, and the dashed cursor is at 11.2391 meters. The difference value is 10.1497 meters. This is the value that we've been looking for. Therefore, this cable is 10.1497 meters long, about 150 millimeters longer than the 10 meters nominal length. We can also measure the return loss of each mated LCPC connection, as well as calculate the insertion loss through a connector using the vertical cursors. The return loss values are displayed in the upper right corner of the software. PC or UPC connectors typically have return losses of less than minus 45 dB, and APC connectors are typically less than minus 55 dB. As you can see, the solid cursor's return loss is minus 56 dB, and the dashed cursor's return loss is minus 53 dB. We can also use the vertical cursors to measure the insertion loss through a connector. To do so, place one marker and integration region so that it covers the Rayleigh scatter behind the connector being measured, and the other cursor and integration region so that it covers the Rayleigh scatter before the connector being measured. The difference value will indicate the one-way insertion loss through the connector. Doing this, we can see that the insertion loss through the second LCPC mated pair is 0.37 dB. Typically, insertion losses of less than half a dB are considered good connections. Therefore, based on our return loss and insertion loss values, the mated LCPC connection at the end of the fiber under test is a good quality connection. In this video, we covered the significance of the group index value and how to set it, as well as how to set the x-axis units. We also took a measurement which demonstrated how to measure the length of a fiber optic cable, as well as how to analyze the quality of connections along that cable using the vertical cursors. This is just scratching the surface of what the Lightwave Analyzer can do. I hope that today I have given you some pointers to help you get the most out of your instrument, as well as the confidence to start taking measurements on your own. Thank you.